Phenol itself is a low-melting, colourless solid, having a characteristic odour.
The old name for benzene was phen, so its hydroxyl derivative is called phenol. Like many other trivial names, phenol is an acceptable International Union of Pure and Applied Chemistry name. As a derivative of benzene, phenol can also be called hydroxybenzene. Benzenol is the systematic name for phenol. Phenols substituted at the phenyl ring are named by indicating the name and the location of the substituent. Numbering of the ring begins at the carbon bearing the hydroxyl group and proceeds in the direction that gives the lower number to the next substituted carbon. 2-bromophenol and 3-chloro-2-nitrophenol are examples of substituted phenols. Phenols containing 2 hydroxyl groups are named benzene diols, for example, benzene 1,2-diol.
As we already know, the oxygen-hydrogen bond has a polar nature due to the electronegativity difference between the oxygen and hydrogen atoms. This enables phenols to form hydrogen bonds with other phenol molecules and with water. Thus, phenols have a higher melting and boiling point and are more soluble in water than arenes and aryl halides of comparable molecular weight. Phenol is a much stronger acid than either aliphatic alcohols or water.
While the pKa values of most alcohols fall in the range 15 to 20, and for water it is 16, pKa for phenol is around 10. Phenols are more acidic than alcohols because the phenoxide anion is resonance stabilized. Since the phenoxide ion is relatively more stable than the undissociated phenol, the equilibrium for the ionization of phenol is shifted to the right relative to the ionization of aliphatic alcohols. The delocalization of electrons in the phenoxide ion is represented in the following resonance structures. We're able to see that the negative charge is delocalized from oxygen onto the aromatic ring. Substituted phenols can be either more acidic or less acidic than phenol itself. Phenols with an electron-withdrawing substituent are generally more acidic, because these substituents can further stabilize the phenoxide ion by delocalizing the negative charge. Examples of electron-withdrawing groups are the nitro group and halogens. Phenols with an electron-donating substituent are less acidic, because these substituents destabilize the phenoxide ion by localizing the charge. An example of an electron-donating group is an alkyl group. Because of the higher acidity of phenols compared to aliphatic alcohols, aqueous sodium hydroxide converts phenols into their salts, producing water-soluble sodium phenoxides. The corresponding reaction of cyclohexanol with aqueous sodium hydroxide does not occur, since this aliphatic alcohol is an even weaker acid than water. But both phenols and aliphatic alcohols can react with metallic sodium to form phenoxides and alkoxides respectively, together with the evolution of hydrogen gas.
We have learned that the bromination of phenol in aqueous solution gives an observable change through the formation of the white precipitate of 2,4,6-tribromophenol. This reaction is often used as an identification test for the presence of phenol. Another instant test for the detection of phenol is the use of an aqueous solution of iron trichloride, which gives a violet coloration.
Phenol reacts instantly with bromine in an aqueous solution producing 2,4,6-tribromophenol in quantitative yield. No Lewis acid catalyst is required for this reaction. The latter derivative of phenol is not soluble in water and forms white precipitate. Another important method used in the detection of phenols is the reaction with aqueous iron trichloride. In this reaction, phenol, or its derivatives, cause a violet coloration of the solution due to the formation of complex molecules.